Welcome to Jeremy's IT Lab. This is a free, complete course for the CCNA. If you like these videos, please subscribe to follow along with the series. Also, please like and leave a comment, and share the video to help spread this free series of videos. Thanks for your help. If you want more labs like this, I highly recommend Boson Software's NetSim for CCNA. NetSim is a network simulator like Packet Tracer, but it's far more powerful and contains over 100 detailed, guided labs covering the CCNA exam topics. If you want to get NetSim, follow the link in the description. In this lab, we will configure a GRE tunnel between R1 and R2. Both routers are connected to a service provider network, but the GRE tunnel will create a virtual direct connection between them. Now, all traffic between R1 and R2 will still have to physically pass through the service provider network. However, all packets will be encapsulated in additional headers to create a virtual tunnel that the original packets pass through. Now, as I mentioned in the lecture video, GRE doesn't encrypt packets, so it's not secure on its own. However, the purpose of this video is just to demonstrate how tunnels work, so I picked GRE because it's quite simple to configure. So let's get right into configuring GRE. On R1 first. Enable conft. To configure a GRE tunnel, we have to make a tunnel interface. This is not a physical interface, of course, but a virtual interface like a loopback interface. Interface tunnel 0. Okay, I have created the tunnel interface. Now I just need a few commands to complete the GRE configuration. First, tunnel source. And now we have to specify which physical interface on R1 will be used for the tunnel. Well, we should use the interface connected to the service provider, so G000. Next, tunnel destination, and then we have to specify the IP address of the other end of the tunnel, so R2. So I'll enter R2's WAN interface's IP, 200.0.0.2. And finally, the virtual tunnel interface itself needs an IP address. IP address 192.168.1.1, 255.255.255.252. Okay, that's all the configuration needed. Tunnel source, tunnel destination, and then IP address. Let's check the status. Do show IP interface brief. Okay, the tunnel 0 interface is up-down. Why down? We'll investigate that after configuring R2. So let's do the same thing on R2. Enable conft interface tunnel 0, tunnel source, and just like on R1 it will be G000. Tunnel destination, this time it will be the IP address of R1's WAN interface, 100.0.0.2. And finally the IP address. IP address 192.168.1.2, 255.255.255.252. Okay, that's all. Let's check the status. Do show IP interface brief. Okay, there's the tunnel interface, but it's still down. Why is that, even though we've configured both sides? Let me show you. Do show IP route. So R2 doesn't have a connected route for its tunnel interface, of course, because the interface is still down. It has connected routes for its physical interfaces, but we're missing a critical route. R2 doesn't know how to reach the IP address we specified as the tunnel destination, 100.0.0.2. If R2 doesn't know how to get to 100.0.0.2, it can't build a GRE tunnel to 100.0.0.2. So let's fix that. Exit. I'll just configure a default route. IP route 0.0.0.0, 0.0.0.0, 200.0.0.1. Okay, after we have the route to 100.0.0.2, the tunnel interface comes up. Let's check. Do show IP route. Now we have the connected route for the tunnel. Let's try to ping our R1 side. Do ping 192.168.1.1. The ping still isn't working, even though the interface is up and we have a route. Actually, the reason for that is that we also have to configure a route on R1 to 200.0.0.2. Let's check the routing table on R1. Do show IP route. Only connected routes for its physical interfaces, so it doesn't know how to get to the tunnel destination, 200.0.0.2. I'll configure a default route here too. Exit. IP route 0.0.0.0, 0.0.0.0, 100.0.0.1. Okay, now the tunnel interface comes up, and this time a ping from R1 to R2's tunnel interface should work. Do ping 192.168.1.2. As usual, the first few pings might fail, because the ARP process is a bit slow in Packet Tracer. But after ARP completes, they will succeed. So, although R1 and R2 aren't directly connected, they will behave as if they are directly connected through the GRE tunnel, and soon you will see what happens when we activate OSPF. But first, let me show you a ping in simulation mode. Okay, I'll do that ping again. Ping 192.168.1.2. Okay, let's check the contents of this message that R1 sends. Click on Outbound PDU Details, and let's scroll down to the bottom. So there's the ICMP message, the ping. It's encapsulated with an IP header, source 192.168.1.1, and destination 192.168.1.2, so the addresses of the tunnel interfaces. But then, on top of that, there is a GRE header, and on top of that, there is another IP header. In this outer IP header, the source IP is 100.0.0.2, R1's G000 interface, and the destination IP is 200.0.0.2, R2's G000 interface. So we call this a tunnel. The original packet from R1's tunnel interface to R2's tunnel interface is encapsulated within an additional IP header, which is used to transport the original packet over the service provider network to reach R2. Now, something you can do when R1 and R2 are virtually directly connected like this is make them OSPF neighbors to share routes. First, let me demonstrate that a ping from PC1 to PC2 doesn't work. Ping 10.0.2.100. Let's wait a bit for all the pings to go through. They should fail. But when R1 and R2 become OSPF neighbors, they will learn each other's routes, and PC1 and PC2 will be able to communicate over the GRE tunnel. So let's enable OSPF on R1 first. Router OSPF1. I'll enable it on the tunnel interface, but also the G00 interface, so that it tells R2 about its connected LAN. Network 192.168.1.1, 0.0.0.0, area 0. That enables OSPF on the tunnel 0 interface. Next, G00. Network 10.0.1.1, 0.0.0.0, area 0. And I'll make G00 a passive interface, since there are no neighbors connected to it. Passive interface, G00. Okay, now I'll do the same on R2. Router OSPF1, network 192.168.1.2, 0.0.0.0, area 0. Network 10.0.2.1, 0.0.0.0, area 0. And again, I'll make G00 a passive interface here, because there are no OSPF neighbors connected to it. Passive interface, G00. Okay, and as you can see, R1 and R2 have become OSPF neighbors. Let's check the routes. Do show IP route. Okay, it learned a route to 10.0.1.0/24, R1's LAN, via the Tunnel 0 interface. And I'll go back to check on R1 also. Do show IP route. Okay, it learned a route to 10.0.2.0/24 via the Tunnel 0 interface. Okay, let's try that ping from PC1 to PC2 again, and this time it should work. Ping 10.0.2.100. One or two pings might fail, but after that they will work. R1 will encapsulate the packet from PC1 using GRE and send it over the tunnel to R2. Okay, in this video, I introduced GRE tunnels. You don't need to know this for the CCNA exam, but it's simple to configure and hopefully help you understand a little about how tunnels work. That's all for this lab. Now let's take a look at a bonus lab in Boson Software's NetSim for CCNA. Okay, here's today's Boson NetSim lab preview. Now, as I said before, GRE configuration isn't a CCNA exam topic. However, it is a CCNP level topic, so I'm going to show you a lab from Boson's NetSim for CCNP, specifically the NRC 300-401 exam. As you can see here, VPN technologies is an exam topic, and they have a lab on GRE tunnels. So let's go through it. This is the lab topology. So there are 3 routers, routers 1, 2, and 3. It looks like router 2 is like a service provider router, and router 1 and router 3 both have their own LANs here. So we're going to configure it so that PC1 and PC3 can ping. Now, we are going to use a GRE tunnel, as you can see here, between router 1 and router 3 to create a virtual direct connection between them. Now there are 3 main tasks. First, configure and verify a GRE tunnel. Task 2 is then configure and verify static routes between R1 and R3 to allow PC1 and PC3 to communicate. And we won't do task 3 in this little preview, but if we do task 3, that is configure and verify EIGRP. So we will replace the static routes with EIGRP. Okay, so let's get right into it on task 1. First, from PC1, attempt to ping PC3. Does the ping succeed? Why or why not? All right, let's try that. Ping 10.10.30.100. Unreachable. We're getting a reply from 10.10.10.1, which is probably R1. Let's see. Yes, so router 1 is saying, I don't know how to reach that network. So that is why the ping doesn't work. Okay, on router 1, create a tunnel interface, tunnel 0, interface, and you can just do T0. That will make the tunnel interface. What do you notice about the state of router 1's tunnel interface? Okay, do show IP interface brief. The tunnel interface is administratively up, so it's not disabled by default, but it's down because it doesn't have a route to the destination. Actually, we haven't even configured a source and destination yet. Okay, on router 3, create a tunnel interface. All right, we'll do the same thing. There we go, and let's assign the interface IPs. So I'll do router 3 first. IP address 192.168.0.2/30. And on router 1 as well. Okay, display IP address and status information about every interface on the router here on R1. Let's do show IP interface brief again. Okay, so the tunnel interface has an IP address, looks good. It's up down still though, so it's not up. And it says to attempt to ping router 3's tunnel 0 interface. Okay, I expect this will work. We haven't even configured any tunnel source or destination yet, so this should fail. Okay, and as expected, the pings are failing. Okay, on router 1, configure the tunnel 0 interface with the source IP address of the interface that is directly connected to router 2. And then we'll configure the destination IP address. Okay, so let's do that. The interface connected to router 2 is serial 00. So I will configure tunnel source S00, tunnel destination. Okay, what is router 3's WAN interface? Serial 00. Here it is. 198.51.100.6. Okay, now the tunnel is up. So I guess it has a route to reach this interface. Let me check. Do show IP route. Yes, it does. It has a static route pre-configured so that it can reach this interface, this network. So the tunnel interface is up on router 1. Okay, we got the destination. Based on the tunnel 0 source and destination configurations on router 1, what IP addresses should router 3's tunnel interface use as source and destination? Okay. Oh, I misread something there, I just noticed. The instructions say to configure the source IP address, not the source interface. So as you can see, with the tunnel source command, you are able to configure the source IP address instead of the source interface. But I just configured the interface itself. So that will actually be incorrect. So I will remove that command and use the IP address instead, since that's what the instructions say. Tunnel source 198.51.100.1. Okay, there we go. Okay, so on router 3, we will configure the opposite. The tunnel source will be router 3's WAN IP address, and the tunnel destination will be router 1's WAN IP address. So let's do that. Tunnel source, first router 3's WAN address is the source. That's 6, is that correct? Yeah, 198.51.100.6. I configured as the destination on router 1 and the source on router 3. Okay. Destination 198.51.100.1. Okay, and the tunnel comes up. In Packet Tracer, this tunnel source command only lets you use the interface. So I already showed you this, but here in NetSim and on a real device, you can use the source IP address. Packet Tracer doesn't support that, so on Packet Tracer you have to use the interface as the source. So that's what I've gotten into the habit of using. Okay, so we configured router 1 and router 2. Configure the source and destination, and let's try to ping. So from router 3, try to ping router 1's tunnel 0 interface. Okay, and it works this time. Perfect. On router 3, display detailed information about the tunnel 0 interface. Okay, do show interface tunnel 0, I guess. So what differences do we notice? Well, it says things like hardware is tunnel, encapsulation tunnel, the tunnel protocol. It's got information here about the tunnel, source and destination, the protocol and transport. It's using GRE, and some other tunnel statistics here. Okay, and then once more from PC1, we will attempt to ping PC3. Okay, the tunnel is working, but we're still getting a destination host unreachable message from router 1. And the reason for that is router 1 still doesn't have a route to router 3's LAN, this network here. And the reverse is also true. Router 3 doesn't have a route to router 1's LAN. So in task 2, we will do that. On router 3, display information about IP routing protocols. What protocols are routing on the router? Okay, do show IP protocols. Nothing, no routing protocols. Examine the topology. Based on what you know about tunneling, on which devices are you most likely required to configure the static route? Okay, well, we'll need static routes on router 1 and router 3 to allow these PCs to ping. Router 3 needs a route to this LAN, router 1's LAN, and router 1 needs a route to this LAN, router 3's LAN. Okay, so let's create those routes. First on router 3, IP route 10.10.10.0/24. And we'll configure the next hop, 192.168.0.1, which is router 1's tunnel interface IP. And then configure the same on router 1. IP route 10.10.30.0/24, 192.168.0.2, which is the tunnel interface IP of router 3. Okay, on router 1, attempt to ping PC3. Okay, so not from PC1, but from router 1. Okay, the ping works this time because it has a route, and router 3 has a return route. Okay, on router 3, attempt to ping router 1's fast Ethernet 00 interface. Okay, so not pinging PC1, okay. Okay, the ping succeeds. And just once more, I'll try that same ping from PC1 to PC3 we did before. It should work this time. Okay, we're getting replies. Okay, so that's all for this lab. So what we did is configure this GRE tunnel between router 1 and router 3, and then configured static routes so that they can reach each other's LAN networks through this tunnel interface. Okay, so that was a quick look at Boson NetSim, this time for CCNP. If you want to get Boson NetSim for CCNA or CCNP, please follow the link in the video description. Before finishing today's video, I want to thank my JCNP level channel members. To join, please click the Join button under the video. Thank you to Thomas, Kwa, Dragos, Tanvir, Charlesetta, Gerard, Tom, Samil, Scott, Martin, Tebogo, Anand, Abraham, Sergey, Unjoku, Victor, Suki, Kenneth, Seamus, Brandon, Marcel, Coney, Donald, Gustavo, Prakash, Nasir, Erlison, Marco, Ed, John, Funny Dart, Velvet Jacob, Boson Software, Devin, Jonathan, and Vance. Sorry if I pronounced your name incorrectly, but thank you so much for your support. This is the list of JCNP level members at the time of recording, by the way. July 22nd, 2021. If you signed up recently and your name isn't on here, don't worry. You'll be in future videos. Thank you for watching. Please subscribe to the channel, like the video, leave a comment, and share the video with anyone else studying for the CCNA. If you want to leave a tip, check the links in the description. I'm also a Brave verified publisher and accept BAT or Basic Attention Token tips via the Brave browser. That's all for now.